In the previous lecture, we completed reviewing theory of probability and theory of random processes to the extent that we will be needing in this course. We also began reviewing some basics of modeling linear single degree freedom systems. So, we studied the response of single degree freedom systems under harmonic loads, under step loads and under impulsive loads. So, under harmonic load, that is if we apply p cos lambda t, as time becomes large, the response becomes harmonic with the frequency coinciding with the driving frequency, and the amplitude of the response varies as a function of mass, damping and stiffness of the system, and this DMF is a dynamic magnification factor which represents the ratio of amplitude of dynamic response to static response, and that is shows a characteristic behavior here. So, in the neighborhood of the driving frequency being close to the system natural frequency, there is a significant dynamic amplification, and this condition is known as resonance, and at resonance the phase, that is this theta, undergoes rapid changes. That is one of the signatures of occurrence of resonance. We called the response of the system to a Hughes side step function as the initial response, and we denoted it as capital G of t, and we have seen already that the derivative of Hughes side step function can be interpreted as a Dirac's delta function, and Dirac's delta function serves as a model for impulsive loads. So, if you apply an unit impulse at t equal to 0, we call that response as the impulse response function, and we showed in the last class that this is actually the time derivative of the initial response. So, this is how the initial response looks for a typical single degree freedom system. So, the displacement amplitude is 1, and this is in steady state it reaches, this value is equal to the static displacement value, as you can see from here. As t becomes large, this exponential decays to 0, and we get g of t as 1 by k, which is nothing but the static response under this unit load. The time derivative of this is shown here. Here the oscillation is about 0, whereas here oscillation is about 1, and this is actually a damped sinusoidal function. Now, we will continue discussing some aspects of dynamical characterization of single degree freedom systems before we take up the problem of response of systems to random excitation. Here we are noting that the effect of applying impulse at t equal to 0 is equivalent to imparting an initial velocity at t equal to 0. That can be verified if you consider the response of a single degree freedom system under in free vibration with initial displacement 0 and initial velocity as 1 by m. If you write the complementary function and particular integral, there is no particular integral, complementary function, there are two arbitrary constants and they can be evaluated using these initial conditions. If you were to do that, you will get a to be 0 because h of 0 is 0, and it turns out that b is actually 1 by m omega d. Following this, we get the solution to this equation as 1 by m omega d exponential minus eta omega t sin omega dt, which we have already obtained by an independent means as the time derivative of the initial response. So, in constructing impulse response functions for dynamical systems, this approach is more easily implementable. The definition of impulse response can be generalized to systems governed by nth order differential equation. So, we have considered second order differential equation. Suppose we have an nth order differential equation as shown here with alpha n minus 1, alpha n minus 2, alpha 1 and alpha naught as coefficients which are independent of time. With the impulse response of this system is given by the free vibration response of the system under these set of initial conditions. Here the field variable h its first n minus 2 derivatives are 0 at equal to 0 and the n minus 1th derivative is unity. So, if you solve this differential equation under these initial conditions, the resulting function will be the impulse response function for this nth order system. Now, what is the use of impulse response function? It can be used to model loads that act over short duration. The duration here is short vis-a-vis the time period of the system, but that is not its main use. The main use of impulse response function is in constructing solution of the system, response of the system to arbitrary loads f of t. For example, f of t is an arbitrary load. This could be, for example, a load induced by an earthquake or a wave or a wind, where we do not have any functional representation in terms of sines and cosines and exponentials, so on and so forth. So, how do we functionally write the solution? See, one can easily write the complementary function, that would not change, but when it comes to writing particular integral, the way we have been proceeding is that we construct the particular integrals based on knowledge of f of t. If it is sin omega t, the particular integral is such and so on and so forth. But if it is an arbitrary function, how to proceed? Now, to appreciate that, we can consider a related problem from statics. Suppose we consider a simply supported beam static under some load q of x. Let us call this end as A, this end as B. The question is, what are the reactions? Specifically, I want to know, say for example, what is reaction at support B. This load is an arbitrary load. So, the strategy we follow is, we consider an elementary strip located at distance x and this is dx. We consider this load q of x into dx is the area under the curve, q of x is rate of loading, load per unit length. So, q of x into dx will have the units of force, and we first consider the response of the beam to this concentrated load. Then we interpret this distributed load as a train of concentrated loads. So, if I want to find the reaction now, I will take moments about point A, and this reaction is actually an incremental reaction. This is not the reaction RB. So, the moment of this reaction about this end, suppose L is the span, will be x into q of x dx. This is the contribution to reaction at B due to this strip of loading. Now, if you consider another strip, there will be another contribution, and the total contribution will be sum of all this. So, we get RB is equal to 1 by L integral 0 to L x dx. So, here if you see, we have utilized the notion of a concentrated force to construct a solution for a distributed load. The concentrated load model in its own right has some merit. It can model loads that act over short areas in relation to the span. The short distributed load can be approximated as a concentrated load, but the main advantage of using the notion of concentrated loads is not so much to model such kind of small patches of loading, but to construct solutions for distributed loading. Okay. Now, in the same spirit, what we do is, when it comes to an arbitrary load in time acting on a single degree freedom system, what we do is, we divide the time axis into a series of impulses. Say we consider a time instant tau and a increment d tau, and this area under this curve is f of tau d tau. This is an impulse. Now, we approximate f of t as a train of impulses. Suppose I am interested in constructing response at time t. So, what I do is first I find out response at time t due to this single impulse. So, call that as dx of t. This is a response at time t, response at time t due to this impulse at t equal to tau, and its magnitude is what? F of tau d tau. Magnitude in the sense area under the curve is f of tau d tau. Now, what is capital X of this x of t? It is response at time t due to several such impulses. So, first and foremost is we have to construct response due to this single impulse and then integrate that from 0 to t. Now, bearing that in mind, we can now consider the response of single degree freedom system under arbitrary loads and certain specified initial conditions. We have a complementary function and a particular integral. The complementary function continues to be, for example, exponential eta omega t a cos omega t plus b sin omega t. The particular integral is what we are constructing. Dx of t is the response due to an impulse whose magnitude is f of tau d tau at applied at tau. See what we have seen, what is the interpretation for h of t? H of t is the response at time t due to an impulse at t equal to 0. Actually this impulse is a unit impulse. Now there are two things that are different here, namely it is not an unit impulse, instead the magnitude is f of tau d tau. Secondly, the impulse is not applied at t equal to 0, but at t equal to tau. So we have to shift time to t minus tau and multiply the response by f of tau d tau. If the impulse were to be applied at t equal to 0 and the impulse was an unit impulse, the answer would be straight away h of t. But now we are applying at t equal to tau and magnitude is f of tau d tau. Now this is response due to that single impulse. So now the total response is summation of response due to the train of impulses, and that becomes integral 0 to t h of t minus tau f of tau d tau. This integral is known as the convolution integral or the Duhamel's integral. Now, how do we evaluate the constants a and b? So, at x equal to 0 I have x naught to be the initial condition. So, using that here I get a. Now, to find x dot of 0 I have to differentiate this with respect to t. There is a slight problem here, you can differentiate this with respect to t easily. First you differentiate this, keep this terms inside the bracket as it is, then exponential eta omega t as it is and the differentiation of this. The first two terms are straightforward. But here the difficulty is the time t appears not only in the integrand but also as a limit. So, you should know how to differentiate an integral with respect to its limit and a parameter inside in the integrand. So, there this is the basic theorem. If you have an integral g of x to q of x f of x comma tau d tau and you want to differentiate this with respect to x, this is the rule for that. So, this is one of the results in integral and differential calculus that you should be aware of. Now, based on that I can evaluate the initial a and b, and if we do that we get this to be the solution. So, x naught, the initial condition x naught is here, x naught dot is here and x naught is here, and this is the response due to f of tau. Now, if you carefully look at this solution, if the system starts from rest, that is if x naught equal to 0, that is this is 0 and this is 0, and if x naught dot equal to 0, the solution is given by the Duhamel's integral, the Duhamel integral. That means for system starting from rest, Duhamel's integral provides the complete solution. It also incorporates in its fold the part of the solution which corresponds to the initial condition x of 0 is 0, x dot of 0 is 0. In that sense it differs from the way we wrote particular integrals in the previous lecture. a small exercise. Let us assume that a single degree freedom system is excited by force f of t as shown here. It is a triangle, this is the origin, this is the time t naught, 2 t naught. The question is, and assume that system starts from rest. Now write the solution in terms of Duhamel's integral. Now if you are in time duration this is, if you are in 0 to t naught, you consider any time t, you have to add the impulses that lie in this interval. So, the several impulses will be here, you have to add. Moment we come here, you have to okay. So, if you are in the region t from 0 to t naught, this will be the Duhamel's integral, because in that region the function is climbing as tau and this is this. Now, if you are in the region t from t naught to 2 t naught, the first expression represents the response due to the rising part, that is up to this part. The second one is from t naught to 2 t naught, that is contained here. If you cross 2 t naught, then that is if you are somewhere here, then the function excitation is 0 from 2 t naught onwards. So, the integration will be from 0 to t naught for this part and t naught to 2 t naught from this part, and then simply free vibration decay. Okay? So, that is what you get here. So, you could use the Duhamel's integral in this manner to construct solutions for arbitrary loads. Now, how do we generalize the notion of Duhamel's integral to nth order differential equations? Suppose I have a nth order dynamical system with excitation as f of t, and the initial conditions are x naught, x naught 1, x naught 2, so x naught n minus 1, so on and so forth. Now, you recall just a while before we defined the impulse response function for this kind of systems using these initial conditions. The n minus 1 derivative at t equal to 0 was 1, rest all were equal to 0. So, h of t would be available for us, and we can continue to use the same logic that we did just now and write the solution as a complementary function plus particular integral. Now, the complementary function will have now n arbitrary constants and n components in your complementary function plus 0 to t f of tau h of t minus tau d tau. This h of t is now solution of this problem. So, the theory of impulse response function and Duhamel integral and construction of particular integrals for under arbitrary loads is more generally valid. It is not just for second order differential equations. Now, we will now revisit the problem of single degree freedom system under harmonic loads, and based on this discussion we will try to now introduce certain frequency domain descriptions of dynamical systems. This impulse response function can be viewed as a time domain description of a dynamical system. So, what is the frequency domain description of dynamical systems? So, we now consider the single degree freedom system, but we now write the harmonic load in terms of complex exponentials, and we consider only the steady state response. So, as t tends to infinity, since the system is linear, it has time invariant parameters and it is driven harmonically, in steady state the response would also be harmonic at the driving frequency, but with a different amplitude. So, we assume the solution to be of this form, and if we substitute now into this equation, so what we get is m h minus lambda square m plus c I h lambda plus k e raised to I lambda t equal to e raised to I lambda t. So, consequently this function h becomes we call h is amplitude. So, h will be 1 divided by this, that is what I am writing here, minus m lambda square plus I lambda c plus k. So, this is the amplitude of response in steady state. we can take out this m and rewrite this function in the form where omega is the natural frequency, eta is the damping ratio, and this function is known as the frequency response function. So, it is the time domain description of a dynamical system. It is a complex quantity, right. Its amplitude would be related to the dynamic magnification factor which we discussed, and its phase will be related to the phase angle that we discussed in the previous talk. Now, the question we can ask is, what is the relationship between the impulse response function and the frequency response function? Are they related? One is a time domain description, other is a frequency domain description. We know that a time domain description of a function and its frequency domain description is related through the Fourier transform pair. I mean, they form a Fourier transform pair. Suppose x of t is the time signal, x of omega is the Fourier transform, they are related by this pair of relations. Similarly, now this is the Fourier transform description of the response, this is the Fourier transform description of the say the excitation. Let us see what we get from this. This omega, please note, is not the natural frequency, it is the frequency parameter used in defining the Fourier transform. So, what we will do now is we will reconsider this Duhamel's integral. So, this is a response of the system under when the system starts from rest under the action of load f of t. Now, we would like to rewrite in a slightly different form. We first thing is I want to write this lower limit as minus infinity. This is admissible because we define the force to act on the system from t equal to 0, and when t is negative we take f of t to be 0. If this is acceptable, I can as well write 0 as minus infinity. Now, you could also write the upper limit as infinity simply because h of t is the impulse response of the system applied at t equal to 0. So, if this argument becomes negative, t minus tau becomes negative, that would happen when this tau crosses t. When tau is greater than t, this argument will be negative. That means, from t to infinity the argument of this function will be negative. That means, it is the response of the system to a impulse which is likely to occur in future. So, that would be 0. Such systems are known as causal system, they will not respond till a load is applied. So, h of t will be 0 for negative t. So, we can therefore write 0 to t as minus infinity to plus infinity. So, we will start with that. We have minus infinity to plus infinity h of t minus tau f of tau d tau. For f of tau, I will write its Fourier transform in terms of f of omega, okay, and we will rearrange this term. I will first integrate with respect to time tau and then with respect to frequency. I will change the order of integration. Now, look at the integral inside the braces. So, I will make a substitution, t minus tau is u, and there will be consequent changes here, and this I omega u, I omega t will come outside because this integral is with respect to u, and if you look at that, it is nothing but the Fourier transform of h of t, what remains inside the brace. This is the Fourier transform of impulse response function h of omega. Therefore, now if you compare this expression with the expression for the Fourier transform definition, x of omega is this, you will identify that x of omega is nothing but f of omega into h of omega. So, in this view graph, this h of omega is the Fourier transform of h of t. Now, this integral is also known as convolution integral. Now, as you see here, we began with a convolution operation and we showed that instead of if you are interested in x of omega instead of x of t, that means if you are interested in Fourier transform of x of t, not in x of t, but its Fourier transform, then this convolution operation can be replaced by a multiplication operation. So, a multiplication is a far easier exercise than evaluating this integral. So, actually convolution in time domain is equivalent to multiplication in frequency domain. So, this notation star is used to denote this convolution operation. When I say h of t convolves with f of t, it means that the value of this quantity is this integral. Now, a convolution operation in time domain is equivalent to a multiplication in frequency domain. So, this is one of the major advantages of frequency domain analysis in linear vibration analysis. Analysis in frequency domain is far easier than analysis in time domain. This is like multiplying or dividing two real numbers. The best way to do it is to take logarithms. The difficult process of division now becomes a process of subtraction. So, in the logarithmic domain you can easily find logarithm of z, and if you are equipped with a table of logarithms and the so called anti-logarithms, you can find out z by working only in the logarithmic domain. In the same sense, we will not try to evaluate this integral in time, but we will go to the frequency domain and find instead of finding x of t, I will find its Fourier transform. Then this is equivalent to finding log z, and then I will do the so called inverse Fourier transform and get x of t as desired. So, this will be effective if and only if the movement from time to frequency and frequency to time is easy. Just like as you have a log table and an anti-log table, you should be equipped with either a table of integrals or efficient algorithms for moving from time to frequency domain and frequency to time domain. The fact is that there are very efficient algorithms known as fast Fourier transform algorithms, which enable you to move from time to frequency and frequency to time. So, herein lies the value of the frequency domain analysis, which we will be extensively using in random vibration analysis. Again, let me emphasize, this is valid only for linear system, because the construction of Duhamel's integral is basically dependent on the system being linear, because we are essentially using a principle of superposition, and that is valid only if system is linear. Now, till now I have defined h of omega as the Fourier transform of h of t, but we also introduced a frequency response function. We were trying to define what is the relationship between impulse response and frequency response function. Now, we will try to continue this discussion. Suppose if we consider the equilibrium equation, and now for x of t I will write the Fourier transform, and if I want x dot of t I will differentiate this. So, this becomes I omega, x double dot of t will be minus omega square into this, and I will substitute this into this and write f of t in terms of its Fourier transform. If I do that, I get this expression, and we get this x of omega, which is amplitude of the response, to be f of omega by m, so on and so forth, and this we already know is f of omega into h of omega. So, if you now compare these two, we see that h of omega is 1 by m omega n square minus omega square and so on and so forth. Now, this is, we have now two interpretations. One is that it is frequency response function, other one is it is Fourier transform of h of t. So, that would mean the frequency response function and impulse response functions form a Fourier transform pair. So, that is what I have written here. This is the frequency response function, and finally, we will notice that if f of t is a unit impulse, the Fourier transform will be 1, and here x of omega will be simply h of omega, right. So, based on all this, the summary of this is that LTI is a linear time invariant system, that means system parameters are not functions of time. So, if a load f of t acts on this system and assume that system starts from rest, the solution is given by convolution integral. This is a time domain input output relation. If you are not interested in time domain, but if you are specifying now the input in terms of its Fourier transform and you are interested in Fourier transform of the output, the corresponding system parameter here is h of omega. So, this is, if you know h of omega, you will get the Fourier transform of the response. Here you should know h of t. If you know h of t, I will convolve f of t with h of t and get my x of t. So, the input output relation here is through convolution. Here input output relation is through multiplication. What are these h of t and h of omega? H of t is nothing but response of the system to a unit impulse, this is h of t. H of omega is nothing but amplitude of the response when you apply a unit harmonic excitation, this is h of omega. So, this f of t and f of omega form Fourier transform pairs, that is this, and x of t and x of omega form Fourier transform pair, and this h of t, that is this and this, also form Fourier transform pair. So, there is a nice picture that emerges which in a nutshell constitutes the input output relations for linear time invariant systems in time and frequency domains. Here I am talking about description of the system, therefore, the question of excitation being random or not does not arise. Okay. So, we have been defining that in terms of impulse excitation and harmonic excitation. Now, we start discussing about response of the system if excitation is a random process. So, the equilibrium equation, the form of the equilibrium equation would remain the same. Here this f of t is a random process. To start with, we will assume that it is completely specified, that means its nth order joint probability density function is known. It is not necessarily stationary, it is not necessarily Gaussian. So, in due course we will be limiting our attention to stationary Gaussian random processes, in which case the complete specification is to mean and covariance. But right now while formulating the problem, there is no such restrictions. What is the meaning of this equation? What does it mean? Here we have a system, f of t is a random process, means this is a collection of time histories. So, you can assume that the system is excited by this time history f of t and it produces a response x of t. This sample would produce one more response time history. This sample will produce another one and this will produce yet another one. So, this system itself is characterized in terms of h of t or h of omega or its equilibrium equation in time domain. So, this will convolve with h of t and produce x of t, this will convolve with h of t and produce this function. So, if this is a random process, that is if f of t is a random process, x of t is also a random process, this is also a random process. Okay. So, when I write this equation mx double dot plus cx dot plus kx equal to f of t with the associated initial conditions, actually this equation itself represents an ensemble of equilibrium equations, because f of t is an ensemble, consequently x of t is also an ensemble. So, this represents a family of differential equations. In a brute force analysis, we can as well take a sample of f of t and get a corresponding sample of f of x of t. So, if the problem is to understand given f of t how to find x of t, it can be envisaged as a large collection of deterministic analysis. Okay? But that is not what we mean by random aberration analysis. What we mean by random aberration analysis is that we are modeling f of t as a random process. That means f of t has certain uncertainties associated with that, and we are characterizing those uncertainties in terms of theories of probability and random variables and random processes. So, we are modeling f of t as a random process. Implicit in that statement is that the uncertainties in f of t have been quantified. We want a similar description of x of t. That means, how does uncertainty measures associated with f of t propagate through the system and produce uncertainty in the response. So, this problem is known as problem of uncertainty propagation. What it means? So, again I will consider the linear time invariant system which are characterized by impulse response function or complex frequency response function. So, one way to look at is just as we saw now, we have samples of f of t and the initial conditions, and we need samples of x of t, right. But other way of looking at is, that means given f of t, x of 0 and x dot of 0, what is x of t? Other way of other questions that we can ask is, given the nth order probability density function of f of t, which actually constitutes the complete description of f of t as a random process, what is the complete description of x of t as a random process? That means what is the nth order probability density function of x of t? A set of much simpler questions would be, if mf of t is mean of f of t, that is expected value of f of t, what is the expected value of the response? If you know the expected value of the input, what is the expected response? Similarly, if you know what is the covariance of f of t, that means you select two time instants t1 and t2, you have two random variables and consider this expectation. If you are given this CFF of t1 comma t2, that is the covariance of the excitation, how do we get the covariance of t1 comma t2? Okay. Now, this is the question that we need to now address. So, starting point for this would be the input output relations in time domain. We will start with time domain because it is more general, it includes transients, it also allows for excitations which cannot be represented in terms of Fourier transforms, so on and so forth. So, the input output relation we have just now discussed can be given in terms of this expression. The first term here is contribution due to non-zero initial conditions, and second one is the Duhamel's integral, which represents the complete solution if system starts from rest. Now, look here, f of t is here, our excitation is here. So, this is actually an ensemble of excitations and that leads to an ensemble of x of t. So, given ensemble of f of t, we can determine ensemble of x of t using this relation. But what is most important to notice here is that the uncertainties associated with f of t propagates through the system and produce x of t, and this propagation of uncertainty in inputs to the outputs follows laws of mechanics. If f of t is Gaussian, how do we say what should be the probability distribution of x of t? To answer that question, you have to write equations of motion using D'Alembert's principle or some variational argument, and then only you can answer that question. That means the subject now combines the quantitative description of uncertainties in the inputs with the theory of vibration analysis to obtain the quantitative description of resulting uncertainties in x of t. So, this is the basic problem in so called stochastic structural dynamics or random vibration analysis. How does uncertainties in inputs propagate obeying the laws of mechanics of the problem? You cannot arbitrarily impose a model on x of t, let x of t be log normal or Gaussian, etc. That kind of free way you do not have. You have to start with modeling the force and allow that to propagate through the dynamics of the system and then arrive at model for x of t. So, let us start now. Suppose I am interested in mean of x of t. So, I will take expectation of x of t, which is expectation of the first term and the expectation of the second term. If we assume initial conditions to be deterministic, they could as well be random, but for our analysis let us assume initial conditions are deterministic. This is an expectation of a constant, therefore, that remains as it is. Now, this expectation includes this f of tau, therefore, I can write this second term as h of t minus tau expected value of f of tau d tau. Expected value of f of tau d tau is a deterministic quantity which is nothing but mean of f of tau. So, the mean of the response is related to the mean of the load through this relation. So, if you know the mean of the excitation, you can find mean of the response. That is, knowledge of mean of the excitation process helps us to determine the mean of the response process. Now, for further discussion, what we will do is we will assume that mean of f of t is 0, and we will also assume that system starts from rest. That would mean x naught and x naught dot are 0 and mf of tau is 0, therefore, mx of t is 0. If they are not 0, for instance, if mf of tau is not 0 or x naught dot are not 0, this is the prescription for finding the mean. So, we are not really losing any generality in our approach if we now set this to 0. If it is not 0, we can always add this component. Now, with that in mind, we will now proceed. The response will now consist of only the Duhamel's integral, because system starts from rest, therefore, this is a complete solution of the system. And now I will consider the expected value of x of t1 into x of t2, that is nothing but the autocorrelation function of x of t. Now, since mean is 0, the autocorrelation function is also the autocovariance function. So, that is given by expected value of this product of these integrals, that becomes double integral, and that is shown here. The f of tau 1 is here, f of tau 2 is here. I can rearrange the terms and we will assume that this integration and this integration associated with expectation are interchangeable. If we do that, the expectation operator can be taken inside the integral and I get this as the expectation. Now, this is a deterministic quantity because it is nothing but the autocovariance of f of t. If we know that through this relation, I can get autocovariance of x of t. So, how does autocovariance of the input translates into autocovariance of the output? It is through this relation, which is nothing but the Duhamel's integral, which has roots in mechanics. So, knowledge of autocovariance of the excitation process helps us to determine the autocovariance of the response process. Now, if you now let this T1 to be equal to T2, the autocovariance function is nothing but the variance, and variance of the response can be written in this form. So, this T1 and I think this is T2, the T1 and T2 become the same, I call it as T, but I still need to know the autocovariance of input. That means, if you are interested in variance of the response and if you happen to know only the variance of the input, you will not be able to determine the variance of the output. That means, given the variance of excitation, you cannot find variance of the response. So, to find variance of the response, you need the autocovariance of the excitation. But if you are interested in autocovariance of the response, the autocovariance of excitation is adequate, right. So, knowledge of the variance of the input is not adequate to determine the variance of the output. Now, we can continue this argument and we can also find higher order moments. Suppose you want the third order moment, expected value of x of t1 into expected value of x of t2, sorry, expected value of x of t1 into x of t2 into x of t3, it will be an expected value of a triple integral. Now, if you know the third order moment of f of t, you can find the third order moment of x of t. Okay, these are higher order correlation functions, we can say call them by that name. So, knowledge of third order moment of the input is adequate to determine the third order moment of the response process. So, you can generalize this and say that for linear time invariant systems, knowledge of nth order moment of the input is adequate to determine the nth order moment of the response process. You must note that this is not generally true, this is true only for linear systems, and if the system is non-linear, you will not be able to do this. If you want to find mean of the response, you will have to know, you will not be able to find that. So, at later in the course I will elaborate, mere knowledge of mean of the input is not adequate to find mean of the response for a nonlinear system. Now, to explain the details of what we discussed till now, let us consider a very simple example. We will consider a dynamical system which is governed by a first order differential equation. You can think of this as a single degree freedom system where mass is extremely small, inertial effects are negligible. So, you can think of this as a half degree of freedom system. If a second order differential equation describes a single degree freedom system, this can be taken as describing a half degree freedom system. So, x dot plus alpha x is f of t, x is scalar, x of 0 is x naught. Suppose f of t is a 0 mean Gaussian white noise process. By that I mean its mean is 0, expected value of f of t is 0, and if you find the covariance, it is a Dirac delta function. So, the question that now I am going to ask is characterize x of t. Okay? Now, first and foremost is we have to write the Duhamel's integral that relates x of t to f of t. For that I need the impulse response function. So, I use the generalized definition of impulse response function. So, this is x dot plus alpha x equal to 0 and this is n equal to 1 and n minus 1th derivative should be 1. So, x of 0 is 1. So, based on that I get h of t is exponential minus alpha t for this system. Okay. Now, therefore, x of t would be the complementary function. To construct complementary function, I take x dot plus alpha x equal to 0 and take x of t as some e raised to st and substitute here I get s plus alpha into e raised to st equal to 0. Therefore, s equal to minus alpha and the complementary function is a exponential minus alpha t. The particular integral is expressed now in terms of the Duhamel's integral. Mind you, h of t is e raised to minus alpha t, it is not that 1 by m omega d sin omega dt e raised to minus eta omega t. Now, I have to find this constant of integration, x of 0 is x naught, so that would mean a is x naught. For purpose of simplification of the discussion, we will take that x naught is 0. If that happens, x of t is 0 to t exponential minus alpha t minus tau f of tau d tau. Now, so I have the input output relation in time domain given by this expression. F of t, as you know, is a 0 mean Gaussian white noise random process. So, we will consider the expected value of x of t and this will be expected value of x of t into expectation of this integral, and if we now take the expectation operator inside, that will operate on f of tau d tau, and this we know is 0, f of tau is 0, therefore, expected value of x of t is 0. Okay? Now, how about covariance? To do that, I take expected value of x of t1 into x of t2. This is this double integral and the expectation operation is inside here, and this we know since f of t is a Gaussian white noise process, I can write this covariance in terms of Dirac's delta function. Now, if you recall, the definition of Dirac's delta function is delta of x minus a dx is f of a. So, integration when there is a Dirac delta function in the integrand is a very straightforward exercise. So, one of these double integrals can easily be evaluated. So, I will replace tau 1 by tau 2 and this integral becomes this. Okay. Now, this is the reasonably simple enough integrand. So, we can evaluate this. So, I will rearrange the terms, I will take out T1 and T2 terms outside because this integration is with respect to tau 2 and I get this expression. This can easily be integrated. So, I get Rxx of T1 comma T2, this is this integral, and if I do this integration I get the covariance function to be given by this. If I now take T1 equal to T2, I get sigma x square of t is given by this expression. So, what we can say about x of t now? X of t is a non-stationary random process. Although the excitation was a stationary random process, the response is non-stationary. But what happens for large times. That is, we have this expression for covariance. In this, suppose if I take T1 becoming very large and T2 becoming very large, but the time lag T2 minus T1 is tau, tau does not become large, T1 and T2 can become large. If I do that, you can see here the first term here will be exponential minus alpha tau, and the second term as T1 becomes large and T2 becomes large goes to 0. So, under this limiting operation, the covariance function, which is function of T1 and T2, now becomes a function of only tau. And what happens to the variance? You put T1 equal to T2, this tau becomes 0 and this quantity is 1, therefore this becomes 1. That you can also see here in this expression, as T becomes large, this exponential minus 2 alpha T goes to 0 and I will be left with I naught by 2 alpha. So, how does this look like? That means we can make some remarks that, now that for small times the response is a non-stationary random process and is dependent on initial conditions. As time becomes large, the response becomes a stationary random process and is independent of initial conditions. So, this reminds us of the steady state that we talked under harmonic excitations for linear systems. So, when this happens, that means as time becomes large, the mean is anyway 0 and the covariance becomes function of time difference, we say that the system has reached a stochastic steady state. So, therefore, we talk about a transient state and a steady state. In transient state, that is in stochastic transient state, the response is a non-stationary random process. In the steady state, the response becomes a stationary random process. That is, mean is 0 and autocovariance function is a function of time lag and variance becomes time invariant. So, this is the definition of a wide sense stationarity, and we agreed that that is our default definition of stationarity. Here is a plot of variance, that is, this is actually sigma x square of t as a function of time. The system starts from rest and there are different alpha here. Alpha, you recall, the system is x dot plus alpha x equal to f of t and this alpha refers to this. So, if you see here, suppose if you follow this red line, we see that for time say up to say 1.5 seconds, the variance is growing and after 1 second it becomes a constant. Similarly, for a different value of alpha, that is this was for red was for alpha equal to 2, the blue is say alpha equal to 1. Indeed, as time becomes large, it reaches a different steady state, and not only that, it takes a longer time to reach the steady state. So, in this transient phase here, the variance is still increasing. So, if alpha becomes still smaller, it reaches a higher steady state, all right, but it takes a longer time to reach that steady state. Okay. So, by depending on value of alpha, there are different steady states possible. Not only that, the time to reach steady state also changes. Okay. So, that is fairly obvious here. If you look at the expression, the time required for sigma x square of t to become constant depends on how fast this function decays to 0, and that is essentially governed by the parameter alpha. Now, we can quickly recall what happened, what would happen if the system is driven harmonically. So, this is a reasonably straightforward exercise. You can write a complementary function and a particular integral and evaluate the arbitrary constant using initial conditions. If you do that, the response of this first order system can be shown to be given by this. This is deterministic. So, here again if you observe this expression, you will see that x of t is aperiodic because there is a exponential minus alpha t term. This part is still periodic, but this part is aperiodic. That means for small time the response is aperiodic and depends on initial condition, that the effect of x naught is still felt. As time becomes large, this exponential alpha t starts decaying and this term goes to 0 and we reach the harmonic steady state. So, there is a good analogy between harmonic steady state and stochastic steady state, transients and what is transient here is non-stationarity there, what is harmonic steady state is stationarity. So, if we were to plot time histories of x of t for same value of alpha, but different initial conditions, we see here that the alpha is same for all these 3 trajectories, but different initial conditions are given. So, they take certain time to reach steady state. So, here we have reached the steady state here, all the 3 trajectories are almost sitting on each other, but they have different transients here. That means, for small time the response depends on initial conditions and is aperiodic, but for large time it becomes independent of initial conditions and it reaches a steady state, in the sense amplitude of this response and the phase difference with the excitation becomes constant. Now, there is another plot here where I have different alphas, but with same initial condition, how different systems take different paths to reach different steady states. So, red graph is for alpha equal to 0.05, it reaches a different steady state, blue reaches a different steady state and this magenta also reaches a different steady state. All of them start from same initial condition. Okay. So, this is how we have a kind of analogy between deterministic steady state and stochastic steady state. So, we will continue with this in the next lecture.